Welcome back to Physical Science 101. This is the fourth and final lesson of Unit 1. This time we're going to be talking about distance and acceleration. We've already talked about distance and average speed. This time we're going to be talking about distance and acceleration. And the distance moved when an object is accelerating is given by this equation. Distance equals 1/2 of the absolute value of the acceleration. And what that absolute value means is that it doesn't matter whether acceleration is positive or negative. It doesn't matter whether you're speeding up or slowing down. If you have an acceleration of plus 5 meters per second, you would write that as meters per second squared. You'd write that as 5 meters per second squared. If your acceleration were negative, if you had an acceleration of minus 5 meters per second squared, you would still write that as 5 meters per second squared. These bars here mean absolute value. That means ignore any minus sign. You can drop any minus sign. So distance is 1/2 times the absolute value of acceleration times time squared. Okay, that's a rather long equation. In symbols, it would be d is equal to 1/2 the absolute value of acceleration times time squared. Now, an important caution is that this equation only works when you are starting from rest or coming to a complete stop. So this equation works whether you're speeding up or slowing down, but only if you start from rest and speed up, or if you're starting moving and come to a complete stop. So only if you start from rest or come to a complete stop can you use this equation. Okay, so let us put this equation to work. Okay, we've already calculated that the acceleration of a car that accelerates from 0 to 60 miles per hour in 6 seconds is 4.47 meters per second squared. That was in the last lesson. The question today is, what distance does the car travel while accelerating? Okay, that is your situation. And you can imagine that this is a car accelerating onto an interstate. So it starts from rest, it accelerates on the entrance ramp to get up to the interstate speed. So draw your diagram, get all of your data out of the question, identify the situation and identify the correct equation, do any unit conversions that you have to do. I don't think you have to do any in this case, but if you had to, you would do that. And then try and work it. And then once you've tried, you can watch me and we can make sure that we're all on the same page. Okay, so here is the situation. Here's the car. And in this case, just to follow the picture, I have the car accelerating down a ramp, covers some distance, and it starts from v is equal to 0, v is equal to 60 miles per hour. And it went from 0 to 60 miles per hour in 6 seconds. So the time here is 6 seconds. And we already calculated that the acceleration was equal to 4.47 meters per second squared. We calculated, you could calculate that now, but we already did calculate that in a previous situation. And the question is, what is the distance? Well, we have an equation for that. We are starting from rest and moving, and so our equation is valid. Our equation distance equals 1/2 absolute value of acceleration times t squared is valid. So our distance is 1/2 times the absolute value of 4.47 meters per second squared times 6 seconds squared. And so our distance is 1/2 times 4.47 times 6 squared. So in this case, since the 4.47 is positive, we don't do anything to it. So it's 1/2 times 4.47 times 6 squared. 1/2, 4.47 times 6 squared. That would be 80.46, which I will round up to 80.5. And let's look at our units. I have meters, and then I have seconds squared divided by seconds squared. So my seconds squared cancel out, and I'm left with meters. And the answer is, the distance is 80.5 meters. Now this particular interstate on-ramp is 320 meters long, which means that you have plenty of distance over which to accelerate. These are the kind of calculations that traffic engineers do when they are figuring out how long these on-ramps have to be, or in the previous example of last time, what the maximum speed can be on a ramp. So these are calculations that are used to keep you safe while you're driving your car. Okay, let's do another example. Okay, here's another question. A falling object has an acceleration of 9.81 meters per second squared. We'll take that as a given for now. Starting from rest, how far does the object fall in 1 second? Okay, let's see what you can do with that. Diagram the situation, get your data, get your right equation, and then do your calculations. Okay, our falling object. Our object is falling. It says we are given that it has an acceleration of 9.81 meters per second squared. And it starts from rest. So its initial speed is 0. And the question is, how far does it fall? So what is the distance if the time is 1 second? So that is everything that we're given. We want to know distance, and we know acceleration and time. So our equation, distance is 1/2 acceleration times time squared. Our distance is 1/2, 9.81 meters per second squared, times 1 second squared. So the distance is 1/2 times 9.81 times 1 squared. So 1/2 times 9.81 times 1 squared, and that would be 4.9, and I've got 0.5, so I can really round either way. It's actually traditional to round to the even number, so that'd be 4.90 meters, and then I have per second squared times second squared, so my second squareds cancel out, so I am done. So when an object falls from rest with an acceleration of 9.81 meters per second squared, in 1 second it will fall 4 meters. Okay, that's one question. Let's ask another question that is similar but slightly different. Okay, here we have a similar but different situation. A falling object has an acceleration of 9.81 meters per second squared, so that hasn't changed. Starting from rest, how much time will it take for the object to fall 15 meters? Okay, so this time we are given the distance and we want to know the time. So let's see what you can do with that one. Okay, once again, we will draw our diagram. It is starting from rest. So it's starting from rest. We're given an acceleration of 9.81 meters per second squared. We are given a distance of 15 meters, and we want to know the time. So we have diagrammed the situation. We've gotten all of our data. It's time to pick an equation. Well, our equation is the same. It is the exact same equation. We have an equation relating distance, acceleration, and time if you're starting from rest. Okay, so that is distance is equal to 1/2 absolute value of the acceleration times time squared. Same equation, but now we are not looking for distance. We're looking for time. What that means is that we're going to have to rearrange our equation. Okay, we want to get time by itself. Well, I have this 1/2 right here. To get rid of that 1/2, I'm going to multiply by 2. Okay, so the 1/2 of 2 is 1, so those cancel each other out. So I have twice the distance is equal to the acceleration times time squared. Now, to eliminate the acceleration on this side of the equation, I will divide by the acceleration. That cancels out the acceleration. So I have twice the distance over the absolute value of the acceleration is time squared. So this side is equal to the square of time. So what I do now is I have to undo the square. And to undo a square, I take the square root. So I'm going to take the square root of time and the square root of this right here. So that gives me 2d over the acceleration, take the square root, is equal to my time. So that is our new thing that we have to do since we're working with time squared. If we want to get the time, we're going to have to take the square root. So now we have solved that equation for time. It's just a matter of putting the data that we have for this specific situation into there. So twice 15 meters over 9.81 meters per second squared. Take the square root is equal to my time. So we can do that calculation. Square root of 2 times 15 divided by 9.81. My number is 1.75. And what are my units going to be? We know they have to come out to be seconds because that's the units of time, but let's look at how that works. Here we have meters per second squared in the denominator, so we flip that over and make that second squared per meter in the numerator, my meters will cancel out. So let me do that over here. So we have the square root of meters times second squared per meter. I'm going to do this for my units. Okay? My meters cancel out, and I'm left with the square root of second squared. So that is units of seconds. So 1.75 seconds equals my time. So when an object falls 15 meters, we expect that object to take 1.75 seconds to fall that distance. Well, that is the end of Unit 1. Next time, we'll start Unit 2. Unit 2 is going to be on forces. So, until then, think science.